stage is yours. This is your presenter.
Okay, perfect. How do I go back? All right. Well, good evening, everyone. I hope you still have a bit of energy for this presentation. My name is Rouze, and I'll be presenting you my work in a Memetic algorithm to solve the Qubit mapping problem on intermediate scale, noisy intermediate scale quantum systems. I guess I can skip the first part about introduction to quantum computing because you're all experts on quantum computing. But I'll have to go through the second part to introduce you to the problem I'm dealing with, and then the solutions I offer here, a Memetic algorithm, and before I draw some conclusions. As an introductory words, we've had a lot of discussions today and yesterday about quantum optimization, which is using quantum computers to solve some optimization problem. And in this discussion, in this presentation, I'll rather do something else. I will define an optimization problem that is, whose goal is to make quantum computing useful. So instead of using quantum optimization for quantum computers for optimization, I will use optimization for quantum computers in a way. So it's the goal is kind of different. So as I said, I can skip this slide. I can also skip this one. You guys know about quantum gates. I just want to point out that the only quantum gate that exists that is made of 2 or more qubits is the CNOT gate, and every other do not exist for my context, because you can always decompose qubit gates with 2 or more gates into sequence of CNOTs. But what I need to introduce is a quantum machine, like the one we're going to see tomorrow, maybe. The current machine for noisy intermediate scale quantum systems, and they suffer from several problems. The first is that they have a limited number of qubits, usually defined as less than 1,000. And with so little qubits, you cannot do error corrections, meaning that you have noisy qubits. So you have errors happening while you execute your quantum circuit. And these errors will come from, for a variety of reasons. It could be the execution of the gates, the measurements that will yield the wrong result, or just coherence, which is the fact that the quantum system evolves even if you don't interact with it. And they have another problem, which is the sparse connectivity of their qubits. If this graph here, oops, sorry. Let me, oops, sorry. Oh, the same shortcut. Yeah, that's what I'm doing. Oh, thank you. And if you look at the graph here, and it represents the connectivity graph of some quantum machines. It represents each vertex of the qubit. Each edge is the possibility to do a CNOT between them. So the qubit 0 can only do CNOT gates with the qubit 1. You cannot do a CNOT between 0 and 2 on this machine. And this will be the main reason behind the qubit mapping problem. So if we consider a little circuit here with one Hadamard gate and 2 CNOT gates and the machine, the object on the left is purely abstract. It's a mathematical construct with qubits, which are just vectors, and gates that are matrices, so it's completely abstract, doesn't exist. But the machine does. It's a physical object that we can observe. So we need to make a connection between the two. And this connection is what I call mapping, and it's choosing a physical representative of my abstract entities. So here, the mapping I've chosen is very simple. I send 0 to 0, 1 to 1, 2 to 2, and this is the 0, 1, 2 mapping that reads as the 0, 1, 2 list. You can read it here. And this is the logical to physical mapping between the two qubits, between the two entities, the circuit and the machine. The thing is, this mapping is not a very good choice. I have a CNOT between 0 and 2 on my circuit, but I cannot do it on my machine. So I will have to change the circuit. Instead of executing the circuit that's on the top, I'll execute the one on the bottom of my slide. These two circuits are completely equivalent in the sense that the quantum state at the end will be the same. So recall that gates are matrices, and these two circuits correspond to the same matrix, in the same Hilbert space. They are equivalent in that sense. but the circuit on the bottom can be executed on my machine with the 0, 1, 2 mapping, because it only involves C0 between 0 and 1, and a swap between 1 and 2, which is just a bunch of C0s next to each other. And this one can be executed on the machine. But I could have made another choice for my mapping. If I had chosen the 1, 0, 2 mapping, that sends 0 to 1, 1 to 0, and 2 to 2, it just corresponds to just reordering qubit 1 and 2 in my circuit, and then I have a connection between 0 and 1, and between 1 and 2, and these two connections already exist in my machine, so I don't have to change my circuit in that case. And I'm telling you, I'm claiming that this second choice is better than the first, because on the first case, I have 6 gates to execute and 5 CNOT gates, and the circuit depth goes to 6, while on the second choice, I only have 3 gates with a depth of 3 as well, which makes the circuit a bit faster to execute. And while at our scale it's not so important, at the scale of the qubits it is, because it limits their ability to, it limits the time they have to decohere, so they will remain coherent. And we also apply fewer gates, which limits the possibility of errors happening in the circuit. And therefore, we can see on this little example that there is a mapping choice that is better than another. And we'll try to make this automatic in the rest of the presentation. So here's a little bit more formal description of the problem. You have an input. The input of my problem is a circuit made of D qubits and a machine with a bit more qubits than the circuit. Otherwise, there wouldn't be mapping between the two that exists. And I'm looking for a mapping between the two, which will be represented by a list of D pairwise integers among the M of my machine, which makes for a large number of solutions. And the cost function, ideally, the thing I want to minimize is the error rate of my circuit, but this is a quantity that is very difficult to compute. One that is a lot easier to compute and related is the depth of the quantum circuit. So this is the thing we'll try to minimize. In the literature, this problem has been approached through several exact methods, and while they work for small circuits, they quickly become very expensive because, remember the previous slide, the number of solutions to explore becomes very large very fast. So heuristics have been designed, and these two that I mentioned here are very, there are a lot more than two, so they take a small place on my slide, but there are a lot more that were designed. I must talk about Sabre for 30 seconds because I'll be comparing myself against Sabre. It's probably the most used one today, one of the most cited paper as well, and it's the one you can find in Qiskit. So we've been using it today and yesterday without knowing it. And there have also been a few metaheuristics developed on this problem, including mine in here bold letters. So there is. This is where I look at myself in the literature. So here's an introduction to the solutions I suggested. I'm using a genetic algorithm. I assume most of you know what they are, so maybe I won't spend too much time on them. And today I'll rather focus on the Memetic algorithm. Again, I assume most of you know what this is. This is basically a genetic algorithm, but instead of doing simply the crossover mutation and repeating these two operations, I've added a local search operator after the mutation operator of my Memetic algorithm, and also by the end of the Memetic algorithm. So once I have decided that I will no longer evolve my generations and my population, I will try to improve it again with this local search operator. In this work, I've decided to go with a 2-point crossover, which is visually presented here. Quick note is that I've chosen a representation that takes the green and red parents and make these two mixed color offspring. Here there is no problem, but there could be problems, such as instead of having the 4075, I could have the 4005 offspring created by my crossover. This is a problem because I can have a 0 twice in a mapping, so I would need to repair the offspring. This is something that I'm hiding here, but there's a bit of work. We also have the mutation. Again, it's a very generic operator. We don't spend too much time on it. It's just a random reassignment of some qubits. What's a bit more interesting is the local search that we developed. And the local search works as follows. So if you consider here the mapping 4125, sorry, on this circuit and this machine, a neighbor because the local search means to explore a certain neighborhood and test all of them and take the best one, is here defined as, so here the neighbors is here defined as picking replacing one value by all available values that are neighbor in the graph. So here 4 can be replaced by either 1 or 7, but 1 is already taken, so it can only be replaced by 7, and that gives us our first neighbor. And the same goes for the others. So 1 can be replaced by 4, 2, or 0, but 4 and 2 are already taken, so I can only replace it with 0, etc., etc. Which means that these individuals are in total the 5 neighbors that are given here, no more, no less. And I will test them all and pick the best one. This is what the local search does. And usually local search are iterated until they converge to a local minimum. I technically could do this, but it would increase the computation time by a lot. And I mean, a lot. So instead, the local search here is only done once. So I have my individuals, I will make the crossover, the mutation. And for each individual, I will explore their neighborhood once, pick the base neighbor for each of them, and then stop and continue the genetic algorithm parts of the algorithm. To evaluate the performance of my algorithm, I will test these 3 types of circuits for GHZ, all DJ and GHZ, and 2 different sizes, 80 qubits or 120 qubits, which also makes a bit of a difference with what you can find in the literature, in the sense that most papers focus themselves with circuits made of less than 20 qubits. So here is a bit more, and I'll have to map that on this connectivity graph, which is the one of the IBM Eagle machine. And the reason why I chose this one is because it's a real machine that is large enough. There isn't much more reason behind this. So in a previous work that was published last year, we evaluated a bunch of parameters for a genetic algorithm alone. So there will also be mention of this genetic algorithm. The goal is to be better than the genetic algorithm because we're doing strictly more work. So if the local search did not improve anything, it would be a waste of time. And we'll also test different types of hybridization, so different memetic algorithms. One where I only do the local search after the mutation. The one where I only do the local search after the final generation. One where I do both. And finally, one in which I do the local search 10 times after the final generation. And the reason why I do it 10 times and not 20 or 5 is because it matches the execution time of the longer version here. So I wanted to make the comparison fair in terms of time. If we look at the result, we have it here in blue, the best found solution, and in gray, the one found by Sabre, so the heuristic against which I want to compare myself, and the final line here for the PGA. So the goal is to beat this genetic algorithm, and ideally to beat Sabre as well. We can notice that the PGA beats Sabre on the first 4 algorithms, and that the 4 version of the PMA, so memetic algorithm, beats the PGAs, so that's the first goal. It also beats Sabre on the first 4 instances, and it doesn't on the last 2, which are the GHZ instances, especially in the GHZ80, for which Sabre is exceptionally good. That is because the circuit has a very specific property that makes 83 is actually the global minimum, and Sabre can find it, but our memetic algorithm cannot, and that leads to very bad solutions. There is, for this specific instances, a very simple solution that anyone in this room can find in under 5 minutes with a pen and paper. And we can also notice that the final remark is that the FIN 10 version, so the one that does the local search 10 times, is the better version, which is a good sign because it shows that the local search did improve its job and it actually improved our individuals. So it was a good definition for a local search. If we look at the execution time quickly, we can notice, however, that so there are two columns for each instances, and maybe the most interesting one is the second, the ratio, which shows how slower the various PGA PMAs are compared to the Sabre version. And you can notice that it can be up to 60 times slower, so it's very much slower, but it's only 60 times slower, thanks to parallel computing. I skipped over this part because this isn't the goal for this talk, but we can talk about it later, or if you have any questions on this part. And even if it's 60 times slower, it remains within a few minutes. And the goal is to remember the goal, finding mappings that leads to circuits that are within acceptable error rates. So if you have a very fast solution, but with a very high error rate, well, you have a useless solution. So maybe you can wait a few minutes instead of a few seconds to get a better solution. At least that's our stand. Finally, we can also notice that the PGA and the PMAs are a bit more robust, in the sense that the variability of the one execution to another is smaller. In these little box plots, you can notice that the Sabre one is you can't read anything probably, but the Sabre is always the fifth box plot of each picture, and the box plot is always larger. So Sabre has a large variability, while the memetic algorithm or genetic ones don't. So they are a bit better in the sense that if you only run them once, you are guaranteed to have a good solution, while Sabre can be sometimes very good, sometimes a bit worse. So conclusions. So we've noticed how a good mapping can reduce the error rates of quantum circuits. We've shown that the PGA and the PMA mostly outperform Sabre, but only on certain circuits, at the cost of being quite slower. It is also more robust, so it also always improves, it has less variability in between executions, and the hybridization of the local search. So the PMA can beat the PGA thanks to the hybridization, so it was a good local search definition. We'll, in the future, extend this work by trying to improve the cost function, namely adding more information to pick even better solutions. We'll also consider multi-objective cost function, because depth is not the only important factor to take into account to consider the error rate of the circuit, as well as try and define problem-specific initialization of the population, and namely with the goal of not being completely far from the 83 solution that we have here on the GHZ80. Our solutions are currently very bad compared to Sabre, so we will try to have a good initialization that will try to balance the gap between the two methods. We will also try some other formulations. This is just a few ideas that we have. Thank you for your attention. If you have any questions. One has any questions? Guess you're all tired. I can understand that.
Thank you very much for your talk.